Recording. All right. Hi, everyone. Welcome to second lecture. So today we're going to, the first half, we're going to do a review of mixed states and density matrices. Large part because some of it is on your problem set, so it'd be good to review that and make sure everyone's on the same page. And then in the second half, we're going to launch into like the first unit of this class, which is on state tomography. So hopefully we can get to that and cover all of that today. So just some quick admin stuff. Problem set 1, it's due on Gradescope on January 31st, 11:59. So the assignment should be up on Gradescope, Hamoon, right?
That's right, yeah.
And so you should be able to, you should have gotten like some sort of email notification that it's like assigned. Yeah, so just make sure to submit to that. There's office hours tomorrow. There's 2 office hours, one at 10 a.m. and one at 2 p.m. It's run by Hamoon, and you should be able to use the same Zoom link as the class. Okay, and for today we'll need 2 scribers. So are there any volunteers for people who want to scribe lecture notes? So we just need 1 person one for the first half and someone for the second half. Okay, so Melody, how about you do the first half and Sandeep, you do the second half? Okay, all right, thanks a lot. Yeah, and next week we have in-person lectures. So the classroom is Chandler 401. So I look forward to seeing you all in person. Okay, so let's jump right into the review of mixed states and density matrices. Oh, there's actually a question. Do we have a recitation section for this class? No. If you know, you want to like ask questions or something, then you can either just bring it up on Slack, or if you want to just like talk to either me or Hamoon, you can just send an email and then we can arrange some office hours or something.
Cool, got it.
Okay. Cool. All right, so in the previous class, we had a very quick introduction to quantum information, and there we introduced quantum states as being described by unit vectors in some C to the D, right? Some D-dimensional unit vector. And these unit vectors are called pure states. And essentially, we should think of pure states as being some kind of deterministic quantum system. And what do I mean by that? So as an example, let's say you take a qubit state, and it's in the 0 state. So remember that the 0 state is this 2-dimensional vector that's represented like this. And let's say we apply a unitary to this qubit, in particular this Hadamard unitary, also known as the Hadamard gate. Hadamard gate. So if you apply the Hadamard gate, you get another qubit state, and it will be this particular qubit state. And I'll just write it a couple different ways if you haven't seen it before. In particular, it's this uniform superposition between ket 0 and ket 1. And if you're not familiar with you know, quantum information, or you haven't seen it that much, then it's tempting to think of this state, which is also known as the plus state, this state as being some like probabilistic state. And you might think that because if you measured the state in the standard basis, you would get ket 0 or ket 1 with equal probability. It's like a coin flip. But in some sense, that's the wrong way of looking at it, because you're just measuring it in the wrong basis. If you remember from last week's lecture, we said actually there's a different measurement you can make on this qubit where you would get a deterministic outcome. Right, but you can measure it in this other basis. And this is also known as the diagonal basis. This is just the basis that's spanned by the plus state and some orthogonal state, let's call it the minus state. Okay, so clearly, like, if you measured in this other basis, since the plus state is one of these basis vectors, you're going to get that outcome with probability 1. So in that sense, it's kind of like a deterministic quantum system. But in quantum information and in quantum physics, we sometimes want to talk about systems that aren't deterministic in the same way. And we need a new formalism to describe those types of random states. And that's what mixed states and density matrices are for. So there's a lot of reasons to have this new formalism. One is, like I just mentioned, you want to talk about probabilistic mixtures of these pure quantum states. Oftentimes we want to talk about noise, which is, in practical quantum computing, this is, of course, very important, right? Noise is unavoidable, and it's always random. And so you want to talk about what happens if some noise affects the state of your quantum computer. And pure states are not going to cut it because you don't know exactly how exactly the noise corrupted your quantum system. Even if you don't want to think about like noisy quantum systems, even if you're like in this ideal situation where there's no noise, you still need this another formalism. And that's when you want to talk about subsystems of quantum states. So imagine that you have 2 qubits and they're entangled, right? What does it mean for the state of 2 qubits to be entangled? It means that you cannot write this as a tensor product of some state psi tensor some state theta, right? That's the definition of being an entangled state. And what that means is if you look at just one qubit by itself, right, like let's say the left qubit, there's no pure state that you can assign to the left hand qubit, right? You need some other way of describing it, and that's what density matrices are for. So for all these reasons, we need to introduce this new formalism. I see we have a question. Rockwell is asking, do we generally have the ability to measure in any basis we want? Theoretically, yes, but practically, no. And if you had like unlimited resources, then there is some change of basis you can perform on your quantum system to measure in that basis. That corresponds to applying some unitary matrix on your system. Unitary matrices correspond to change of bases. But generally speaking, most unitary matrices are going to be too complicated to implement in any reasonable amount of time. But at least in principle, you can implement it. So hopefully that makes sense. Okay. So let me just spell out motivation number 1 when I want to talk about these probabilistic mixtures. So let's say someone walks up to you, they flip a coin, and depending on the outcome of the coin flip, they either hand you a qubit that's in the state 0 or a qubit that's in the state plus. if you don't see this coin, then how do you describe the state that's given to you, right? You don't know exactly which state it is. And it's this probabilistic mixture, 1/2 probability of being ket 0, 1/2 probability of being ket plus. Okay, so this is what we mean by a mixed state. It's just a probability distribution over pure states. Okay. Motivation number 2, actually, I think I kind of described it. Like here is an entangled 2-qubit state known as the EPR pair, right? It's the equal superposition between both qubits in the state 0, 0, or both qubits in the state 1, 1. You cannot write this as the tensor product of 2 individual qubit states. And so how do you describe the state of the left qubit, for example? Okay, so let's do some quick linear algebra review, just so we have enough to understand what density matrices are. So first, let me say what the spectral theorem is. So this says that, let's say you have a Hermitian matrix. So you have a D by D Hermitian matrix. Then you can always write it as essentially, you can diagonalize it. So there exists some orthonormal basis. Let's say ket B1 up to ket BD. It's a d-dimensional orthonormal basis. And you have real eigenvalues lambda 1 up to lambda d, such that your Hermitian matrix A can be written as the linear combination of your jth eigenvalue, lambda j, times the projection onto the jth basis vector. Every Hermitian matrix can be diagonalized in this way. All right, so hopefully that should ring a bell for most people. So that's the spectral theorem. The notion of positive semi-definite matrices, this is a special class of Hermitian matrices. Hermitian A is positive semi-definite, or PSD, if and only if all of its eigenvalues are non-negative. Okay. All right. Hopefully no questions about this. So that's, I think, all the linear algebra we'll need. So now we can finally define what a density matrix is. It's the mathematical formalization of a mixed state. So instead of talking about vectors, we're now going to represent states using matrices. So a d-dimensional density matrix is some row such that it's positive semi-definite. So in particular, it's Hermitian. And the trace of this matrix is equal to 1. Okay. Density matrices describe mixed states in the following way. So if you have a pure state, some unit vector psi, then the density matrix corresponding to that will be the outer product ket psi bra psi. Okay, so this is it's the outer product. If you remember from last time, It's also a projection onto the state psi. So that's the pure state case. If you have a mixture over pure states, like a mixture psi1 with probability 1, psi2 with probability 2, and so on, then you can package this all into the density matrix by taking this linear combination of the pure states weighted by the probability of that pure state. Right? So let's just quickly make sure that this is actually a density matrix. So let's first check the trace condition. So the trace of rho, let's say this is rho, is going to be the trace of the sum of pi psi I. Trace is linear, so we can pull out the sum over I. And we have trace of this rank 1 outer product. And this is the same thing as sum over pi. This trace is 1. Right? So if you take this rank 1 outer product of a unit vector, the trace of this matrix is going to be 1. And the sum of these probabilities is going to be 1 because all of these probabilities have to sum up to 1. So we verify this trace condition. And we just have to check that it's positive semi-definite. This is PSD because you're taking a linear combination of rank 1 outer products, each of which are positive semi-definite, and you're taking non-negative linear combinations of them. Any questions about this so far? Just want to make sure that we all understand.
I have a question. Does this mean that any two mixtures with the same density matrix are indistinguishable? Like, is this something we assume?
Oh, good. It's not something that we assume, but I'll get into this in like 2 slides.
All right.
Yeah, but that's definitely a very important thing. Any other questions about just at least the bare definition of density matrix? Okay, so let's do just a couple of really quick examples to make it really concrete. So let's say we have these 2 pure states, these qubit states, ket0, ket1, and let's just write out what the density matrices corresponding to these are. So ket0 would correspond to the outer product ket0 bra0, and this is just the product of the column vector with its row vector self. You do the vector-vector multiplication, and you get this matrix. And clearly, you can see that it's a density matrix. It's trace 1. It's positive semi-definite. Similarly, ket1 bra1 is equal to this density matrix. Right? Okay, so what about a more interesting example? Let's talk about the example from a couple slides ago. Someone flips a coin, gives you either ket0 or ket plus. So what's the density matrix corresponding to that? Well, let's just take 1/2 ket bra0 plus 1/2 ket plus bra plus. We already saw what the first term looks like. So this is just 1/2 0 0 0 plus, and if you you work out the math, you get this. This is equal to, let me try to do it good quickly. I think this is, yeah. If you worked out what the plus state corresponds to. It looks like this. You sum up the two matrices, you get 3/4, 1/4, 1/4, 1/4. So when someone hands you this unknown qubit state, they flip this coin behind the back, you get this single qubit. The best way for you to describe the state of this qubit is this matrix. It describes essentially your uncertainty about what the state is. Okay, two more examples, and this will get to, I think it was Dean who asked the previous question. So here are two more mixtures. Here's the mixture of 1/2 ket 0, 1/2 ket 1. What's the density matrix corresponding to this? We'll just do this real quick. Right? If you sum this up, you get 1/2, 0, 0, 1/2. This is the identity matrix divided by 2, right? This density matrix, the identity matrix, has a special name. It's called the maximally mixed state. And whenever you see a density matrix that's the identity matrix, essentially it kind of means it's like a completely random state. You have no information about it. It's sort of featureless. So that's what it is. Let's look at this second state here. It's a mixture of ket plus and ket minus. So we already saw what the ket plus matrix was. This is 1/4, 1/4, 1/4. And if you add in the minus state, and let's remind ourselves what the minus state is. It's the equal superposition between 0 and 1, except there's a minus sign in front of ket 1. So you look at the outer product corresponding to this, and you get the following density matrix. And notice that this density matrix has negative entries, right? Okay, so you sum this up, and lo and behold, you get the same matrix. So it's the same density matrix, but from two different mixtures. And that might seem kind of odd, but what this is telling you is that there's no way to distinguish between the first mixture and the second mixture. If the density matrices corresponding to two mixtures are the same, then there is no physical experiment, no matter how much resources you have, to distinguish between the two mixtures. They're physically the same thing. So that's a really important thing to keep in mind.
I have a question about density matrices. So is it possible for like a certain mixed state that one or both of the properties of a density matrix is not satisfied? And like if that happens, does that mean that like that mixed state is undefined?
So are you asking if you took a mixed state, which is like this mixture of pure states, and you formed the density matrix from it, that for some reason it's not actually a density matrix?
Yeah, like the trace is not equal to 1, or it's not positive semi-definite or something like that.
Right. So it'll turn out that if you use the recipe that I described earlier, it will always be satisfied, like those two properties, as long as the probabilities sum up to 1, and you're summing up these rank 1 outer products, which they're always positive semi-definite matrices. So so when that happens, the two properties will always be satisfied. Does that make sense?
Yeah, thank you.
Rockwell?
Yeah, I don't know if maybe you're getting to this, or maybe this doesn't isn't a meaningful question, but is there a way to sort of like read the density matrices? Like if you look at index ij, does that tell you something about a certain state, or does it not make sense to really look at it that way?
That's a really good question. Yeah, maybe let's pick kind of an exotic example. Where's my pointer? Oh, there it is. So this is one density matrix, this is another one. And you're kind of asking, like, if I look at this, like, how do I interpret these different entries? Yeah. So first of all, when you look at a density matrix, okay, in this qubit example, the rows and columns are indexed very naturally. They're indexed by the ket0 and ket1 basis. So this entry here corresponds to, you can think of it like the probability of this density matrix of this quantum state being in the ket0 state. So in this case, the yeah. Oh, okay, sorry. This is not a valid density matrix because it does not trace one. That's because I've sort of already multiplied this probability 1/2 in front, so maybe that's a little. Okay, then just to make things super clear, this is the same as I mean, it's the same numbers, but I've just factored out the 1/2, okay? But just to make it more clear. So if we look at this density matrix right here, it's positive semi-definite, has trace 1. This entry just means if we measured this quantum state in the standard basis, the probability that we get the ket0 outcome will be 1/2. Okay. This 1/2 means the same thing, but for the ket1 outcome. So the diagonals have a very clear interpretation. It's just the probability if you measure in that standard basis, the probability to get that outcome. The weird part is how you interpret these off diagonals, and it's a sign of how quantum your system is. So if all the off diagonals were 0, then your density matrix just corresponds to a classical mixture of classical basis states. But this 1/2 is telling you that there is some like superposition going on between, let's say, ket0 and ket1. The minus sign tells you what's the relative phase between the ket1 and ket0 states. So yeah, that's some high-level intuition. Okay, really good questions. Okay, so mixtures. Okay, this is just a really quick thing, which is like, let's say I had, I told you about taking mixtures of pure states. You can also take mixtures of mixed states as well in kind of a very natural way. Like, let's say you have two mixed states, rho and sigma, and then a person flips a coin and they say, well, with probability P, they're going to give you this mixed state rho, and with probability Q, they're going to give you mixed state sigma. And they hand you one of those two mixed states. What's the resulting mixed state you get? And very naturally, it's going to be the linear combination of those two density matrices. So P and Q are numbers, rho and sigma are density matrices. This is going to be another density matrix. Okay, so assuming P and Q sum to 1, then this is a valid density matrix. You can check trace of tau is just going to be P times trace of rho plus Q times trace of sigma, which is equal to P plus Q, equal to 1. So you can just combine density matrices in this really natural way. All right, moving on. So let's talk about measurements. Last week, I talked about measurements as like a measurement is like if you had some state and you measured it in the standard basis, then you're just projecting the vector down onto one of its coordinates. But we can also talk about measurements in other bases or general projective measurements. So this is what the formalism is. So a set of matrices, M1 up to MK, is a K outcome projective measurement if each of these matrices is a Hermitian projection matrix. And formally what that means is it's Hermitian, and if you square the matrix, you just get itself. And furthermore, if you add up all these projection matrices, they all equal the identity. So it sums up to the identity. So in particular, it means that all of these matrices are orthogonal to each other. And if you had a pure state psi, let's go back to the vector world for now, just to anchor our intuition. And you measured this state psi using this projective measurement M, then the rule is that you get outcome I with probability that's equal to this formula here. So this is, you first multiply your vector psi by the projection matrix Mi. You get a new vector, but it's not necessarily unit length. And you just look at how long that vector is and square it. That's going to be the probability of getting that outcome. And then there's a post-measurement state, like the state collapses into a different state. And it's just going to be, you got this Mi times psi, it's some vector, and you just have to renormalize it. The most common type of projective measurement is if you took some basis of your space, let's say B0 up to BD minus 1, then the corresponding projective measurement would be each of the MIs would be the rank 1 outer product corresponding to that basis element. Okay, so that's the formalism for projective measurements, but that's with pure states. Okay. All right. So with all that in mind, let's go back to density matrices. Density matrices, like by definition, are supposed to encode everything that's physically relevant about a probabilistic mixture of pure states. If you can't learn it from the density matrix, then you can't learn it at all in some sense. So remember last time I said with a quantum system, there's two things that could happen to it. Either you undergo isolated unitary evolution, or it undergoes measurement. And the same thing is true with density matrices, but now we have some updated rules about how you describe each of these two processes. So if you took a density matrix rho and you let it evolve under some unitary operation, you just have to multiply on both sides by the unitary. Or more specifically, you have to conjugate it by the unitary. Okay, so the new state after this evolution is U rho U dagger. Right? Let's see that this is actually compatible with what we learned last time. So in the pure state case, You started with some vector psi. If it undergoes unitary evolution, you multiply the vector by the unitary, right? So you get a new unit vector. But let's consider taking the density matrices corresponding to these pure states. So this is the mixed state representation. Right? Remember that the density matrix corresponding to the pure state is ket psi bra psi. And when it undergoes unitary evolution, we just multiply u on both sides. But notice that like this is just the rank 1 outer product of this unit vector. Okay, so it's compatible. Okay, so that was with unitary evolution. Now let's talk about measurements. So if you had a projective measurement M, with some outcome matrices M1 up to MK, what happens if you measure a density matrix with this measurement? The rule says you're supposed to get outcome I with probability trace of Mi rho. Again, let's check that this is consistent with what we know about pure states. So let's say rho happened to be a pure state. Then what is trace of Mi rho? Well, this is trace of Mi with the pure state psi. But in your homework, you're showing that this is equal to this matrix Mi conjugated sandwiched by the vector psi, right? But what do we know about this matrix Mi? It's Hermitian and equal to its square. So this is the same thing as this particular inner product. And this is equal to, I claim, the length of this vector. Right? But we saw from the previous slide, this is like in the pure state case, what the measurement outcome probability should be. So again, like everything is consistent. Okay. Any questions so far? All right. So if not, do I want to talk about this? Yeah, I think might as well, because we'll talk about observables later in the lecture. Okay, so some more definitions. Sorry, this is kind of like many definitions, one right after another, but we're going to be using this throughout the rest of the class, so it's kind of important to make sure we understand all of these concepts. Something that comes up very often in physics and quantum information is this notion of observables. And basically, you should just, whenever you see the word observables, you should just think of the word measurement, because that's really what they are. And it's just a more convenient way of packaging what a measurement is. So, mathematically speaking, an observable is just a Hermitian matrix. That's all it is. And it And the claim is that it encodes a measurement. So let's say we have a Hermitian matrix A, CD times D, Hermitian. Remember that according to the spectral theorem, we can diagonalize A. There's some real eigenvalues. There's a basis under which it's diagonalized. Right. And it encodes a measurement in the sense that we can just take this orthonormal basis and consider the measurement corresponding to that. Okay, right, orthonormal basis, you can definitely measure according to that. What are the point of these lambdas? The lambdas are some kind of like weights that you assign to each of the measurement outcomes, right? So think of the following process. You get some quantum state. You measure it in the basis B1 up to BD. And let's say you get some outcome I, like you measured the state BI. Then what you would output as your outcome is going to be the number lambda J. Okay. Did I mean lambda I? I'm using the indexing variable J, so maybe I used I in a previous slide.
Just to, I don't know if I misheard maybe. I think you said if you measure it and you get the basis, you get BI, then you output lambda J.
Oh, sorry. It should, yeah, the indices should be the same. So if you get BI, you output lambda I.
Okay, thanks.
Yeah. Okay, thanks. So the reason we want to package measurements with weights in this way is because if you want to talk about the expected outcome according to these weights, then there's a very convenient mathematical formula, which is the following. Let's say you measure some quantum state rho with respect to observable A, then this is equal to, by definition, trace of A times rho. Let's see why this makes sense. So let's just expand out the definition of this diagonalization of A. So this is summation of lambda J, Bj, Bj, rho. Trace is linear, so let's pull out the sum. And we see that we have this trace of the product of rho times this projector Bj, Bj. Oops. This is just the probability of obtaining outcome Bj measuring rho. So it's sort of like, it makes sense that this is called the expectation value because you weight the probabilities of each outcome by these weights lambda J. Okay. Good. So that's all you need to know about observable. It's just like this convenient way of packaging measurements. All right. Okay, I think we're almost at the end of this review of density matrices. Just a couple more things. Let's talk about density matrices of multiple systems, right? Remember, we have this tensor product notion to sort of talk about composite quantum systems. Okay, so the same thing works here in the density matrix world. Let's say you have two quantum systems. One of them is in the state rho, the other is in the state sigma, right? Then the joint density matrix of both systems is rho tensor sigma. Okay. It's a matrix, a bigger matrix. We also often talk about if you have many copies of a quantum state, right? Then let's say you have n copies, then n copies is abbreviated rho raised to the tensor power n. Okay, this is just the same thing as rho tensor, so on, n times. Right, that's just notation. Just like not every 2-qubit state can be written as a tensor product of a qubit state on the first qubit and another state on the second qubit. Not every composite quantum system can be written as a tensor product of density matrices. But here's a very important difference. In the pure state case, if you couldn't factorize it using the tensor product, we said it was entangled. But that's not the case in the density matrix world. So here's an example. Let's say you have 2 qubits that is described by this density matrix rho. And it's this mixture of 1/2 ket bra 0, 0 plus ket bra 1, 1. And this is, you might look at this and say, oh, this looks very similar to this EPR pair that we saw a few slides ago. So this is not the EPR pair. Right? The EPR pair is a pure state. This is not a pure state. This is a mixed state. And it's just the same as with probability 1/2, someone gave you 2 heads, or probability 1/2, someone gave you 2 tails. And this is just, the 2 qubits are correlated clearly, but they're not entangled in any quantum sense. And we haven't really talked about entanglement much, but one way of saying this is you cannot use this quantum state to, let's say, violate a Bell inequality or do something that you can't simulate using classical information. So this is just something to keep in mind. This is kind of a subtlety, but just because you can't factorize the mixed state doesn't mean that there's quantum entanglement in there. Okay, good. Let's see. So in the last 2 minutes, let me just finish up by talking about partial traces. This will come up in the problem set if you haven't looked at it already. Partial traces are just a way of being able to discard quantum systems. Okay. So let's say you're given a density matrix on 2 systems, one called A, one called B, right? Maybe they're 2 qubits. They don't have to be qubits, but let's just say 2 systems. But you only want to talk about the state of the system on part A. Then to do that, you take the partial trace. So you take the density matrix on AB, you apply some linear map called the partial trace, and then you get another density matrix on a smaller system, and you just get what's called the reduced density matrix on system A. So in terms of dimensions, row A is only going to have dimensions that's corresponds to the dimensionality of system A, whereas this row AB is a density matrix that's bigger. And mathematically, like, how do you define this partial trace? You can define it by linearity. So we'll define it on outer products of this form. Okay, so let's say you have, some matrix that's, this outer product, A1, B1. Okay, so let me be more precise. Okay, so A1 tensor B1, this is a column vector for the system AB, and then you have the row vector bra A2 tensor bra B2. Okay, this is just going to be equal to what's written above, right? Here you just have a matrix, this outer product for system A, and then the B2s they sort of get they get turned from vectors into numbers. So this is a number here. So what you're left with is just a matrix on system A. Okay, let's see. Okay, one final thing before we take a break. Okay, so this is kind of a cool concept, which is, let's say I give you a mixed state, some density matrix, row A. Let's say system A is just a single qubit, right? And you have this mixed state, meaning that there's some uncertainty about exactly what pure state the system is in. But it turns out that there's always some bigger pure state that is not just on system A, but also includes some system B, for which row A is a partial trace of this pure state. Okay. And another way of thinking about it is that if someone hands you a mixed state, there is some other system that's out there which you don't see, the system B, which your mixed state is entangled with, and you're only seeing just part of the entangled state. This pure state, psi, is called the purification of the mixed state that you're given, right? Okay, so that's just something to keep in mind, and this will be something that comes up later. So how about we take a 7-minute break and let's come back at 3:10, and then we can continue with the rest of the lecture. In the meantime, if people have questions, I'm happy to answer anything.
By the way, is the lecture going to be recorded for next week, or what's your plan on that?
Yeah, I'm going to try my best to find a setup that records the lecture. Like maybe I'll try to get some webcam and aim it at the board or something. so that people who are external, or maybe someone is, if they're not feeling well, then they can be able to catch up on the lecture.
Okay, thank you.
I was wondering, the trace that we like the notation for the trace, we've been using B. Are these expressions equivalent whether we are calculating the partial trace of B or A?
It refers to which system you're tracing out. So,
I see. So here, all of these examples are, we're tracing out the system B, or we're tracing out B from system AB.
yeah,
Okay.
if we put out, if here we put A instead of B, like we were tracing out A, then we would sort of convert the A part into a number and leave the B part as a matrix.
I see. Okay.
Yeah.
Got it. Thank you.
Actually, maybe I'll just write it here just so.
Henry, when you trace out, say when you trace B out, the resulting state is not necessarily a pure state, right? Or there's no reason it should have trace one, right?
Oh, great question. If you start with a density matrix and you trace out, you will still have a density matrix.
If you, I see. Okay. So if this, okay, if this composite system that you've described was a density matrix, then you trace it out, then inner product of B to B1 would be 1, and then it would still be, yeah, the trace would still be 1.
Yeah.
Okay. Yeah.
Yeah, maybe I'll just write a comment here. That's a good point.
Thanks.
And I mean, sort of one way to think about that is the partial trace as like a physical operation is very natural. It just means you just ignore one system. So if you started with a physical system, which is a density matrix, you ignore part of it, then the remaining thing should still be a physical system. So has to have a density matrix description. Yeah, Asa?
So I'm still a little confused about the kind of relationship between the density matrix as a representation of a system that is not entangled. Does the density matrix, does it have to represent a system that is exclusively never entangled or not necessarily entangled? Because the fact that you can have a purification, then you said that if you get one state, it can be written as the purification of another system that it's entangled with.
Sorry, could you ask the question one more time? Just wanna
Yeah,
make sure.
so does a state that's represented, or a combination of states that's represented by a density matrix, do they have to necessarily be not entangled, or does the density matrix just not give you any information about the entanglement?
You're talking about in the context of this purification
Yeah.
business. Okay, so I'll say this. So let me go to that slide. So let's just talk mathematically here. If you have a mixed state, row A, that's not really a mixed state. It actually was it's this rank 1 density matrix. So really it's a pure state. Then in this case, it's for sure not entangled with any other system. So that's point 1. I mean, okay, so you know it. So let's say one way of saying that is, let's say there happened to be some bigger pure state on systems A, B. Such that the partial trace of then what that means is that theta AB actually must have factored as psi A tensor. Oh no, that's a bad. So in other words, like if you had a pure state, then this is like the only case in which you're sort of guaranteed that it cannot be entangled with anything else. But if you had a non-pure state, like row A, you know, was like 1/2 something plus 1/2 something else, then you can always find some purification, at least mathematically speaking, for which that purification is entangled across A and B.
Thank you.
Yeah. Okay, so I have 2 more slides on density matrices, and then we can finally get to state tomography. But these are very important slides because we'll use them later today. Okay, let's talk about how do we distinguish density matrices, like how do we measure how similar or how different they are. And there's many different measures you can come up with. All of them are related to each other in different ways. But here's one that's particularly useful, and this is called the trace distance. So it's a function of 2 density matrices, rho and sigma, and you want to measure how close they are. It's equal to this norm between the difference between rho and sigma. So rho and sigma are matrices. If you subtract them, you get another matrix. That difference matrix, you can look at its trace norm. Before saying mathematically what that actually means, here's the operational meaning, which is like far more important to keep in mind, which is that this is defined as the maximum probability that you can distinguish these 2 density matrices using any possible operation. So I give you these 2 density matrices. If you can come up with an experiment that can distinguish between the 2 with probability, let's say 1/2, then it means that the trace distance is at least 1/2. Okay. And if you take the best possible experiment to distinguish between the 2, that is the definition of the trace distance. On the other hand, if there is no experiment to distinguish between the 2 density matrices, then it means that their trace distance is 0. In other words, these density matrices have to be exactly the same matrix. So that's the thing to keep in mind about this trace distance. But okay, what about the mathematical definition? it's defined as trace of this absolute value of rho minus sigma. And this is the matrix absolute value. That's not the same as like taking the absolute value of every single entry. Right, it's not the same as that. It's really the sum of the absolute values of the eigenvalues of the difference. Okay. So that's kind of like the abstract definition, and it's not always easy to calculate because if you take the difference of these two density matrices, you get some other crazy matrix, and it's oftentimes difficult to compute what the eigenvalues are. But this is the formal definition. Okay. Really, the thing to keep in mind is this operational meaning.
Is there a proof of like the fact that like the probability of a distinguishing is exactly equal to this, like to half of the norm of the difference?
Yeah, there is a mathematical proof of this. It basically comes from it turns out that this is equal to there's like a variational expression for the trace norm, and it's like you maximize over the trace of the difference of the two density matrices with some operator that has spectral norm at most 1. Okay. I mean, this is some theorem in functional analysis, but you use that to get this operational interpretation. Okay, so this trace distance has a lot of nice properties. I'm not going to go over them here. You can refer to this later. But it sort of basically satisfies any nice property that you kind of expect that it to satisfy. Like it's symmetric. The distance between rho and sigma is the same as the distance between sigma and rho. It satisfies a triangle inequality. That's really important. And so on. Okay. We'll sort of bring this up as we need it throughout the course. But just know that it's a really nice distance measure, and so that's why we're going to use it often. Okay, so that's the review of density matrices. It kind of took a while, but we'll be relying on it throughout the course. Before I move on, any more questions about density matrices? Okay, good. So let's jump into the second half of this course, state tomography. So this is our first quantum task that we want to analyze. So let's say someone walks up to you and they had a bunch of quantum states, and they're all copies of the same quantum state, but it's an unknown state. Okay, so we're going to represent the quantum state that they have as rho tensor k, because they have k copies of it. And you can just sort of picture like they're just giving you some massive, complicated quantum entangled electrons or something. Somehow they have some apparatus to give this to you. And you want to obtain some classical description of what this quantum state is. So someone gives you this complicated quantum state. You want to perform some operation on this quantum object. This operation is called tomography. And you want to output a classical state. And essentially, you just want to output a matrix. That's essentially the density matrix. So let's say rho is a d-dimensional system. It's a d by d density matrix. Somehow you want to just extract out what is exactly this quantum state. So that's the goal. So here are the questions. Like, first of all, is it even possible to perform with any number of copies? Okay. Maybe it's just not possible. If it is possible, what's the minimum number of copies that you would need of a state in order to get this classical description? And we're going to look at this in the sort of the worst case. We're going to obtain some worst case lower bounds on the number of copies needed. But even when you know the worst case, you might ask, are there cases in which tomography can be made much more efficient so you don't run into this worst case lower bound? So for this lecture and the next couple lectures, we're going to analyze this, look at these questions. Okay, so let's kind of think about this task. So first you might say, why do I even need copies at all? Would it be possible to obtain this classical description if I get only one copy of the state? Okay, there's a question in the chat. I don't fully understand the relationship between copies and difficulty of performing tomography. So I guess, you can think of, maybe imagine that actually creating each copy of a state is resource intensive. So you want to minimize the number of copies that you need in order to achieve this goal. It's sort of a natural natural task. Yeah.
And I guess you need more than one, because the moment you perform a measurement on your state, it already collapsed. And so,
yeah, good. Okay, so you're starting to get into why it seems unlikely that you should be able to do this with one copy of a state, right? You might say, well, we know that if you perform measurement, the state collapses, and then once it collapses, the state changes, and so you won't be able to get the original information. That's true. And that's very good intuition, but you might still wonder, well, maybe there's a more clever thing I could do. Maybe I could, apply some unitary transformation and then measure it a little bit and then measure it again. You somehow have to rule out that. But of course, it turns out that one copy is certainly not enough. Even 2 or 3 or a few number of copies is not going to be enough in general. And we'll see why. We're going to give a formal argument for why it's not possible. And essentially, if it was possible, this would imply an incredible information compression method that's actually too good to be true. So how do we see that? Well, let me take a look at my notes. Right. Okay, actually, yeah, so Yuval was already thinking ahead. Some intuition for why it shouldn't be possible to do tomography with one copy of the state. Remember that yeah, I said early at the end of the lecture last time is that quantum states, they seemingly contain tons of information, like an n-qubit state requires 2 to the n amplitudes to describe, right? So like a very complicated object, but all that complexity is sort of hidden behind measurements, and quantum states are very fragile. Right, so that's why you kind of, so you have to be very careful about what you do to a quantum state to extract information from it. Okay, so, but let's formally argue that if you had a tomography procedure that only used a few number of copies, you would run into some information theoretic impossibility. Let's suppose for contradiction. And now let's just actually focus on pure states to keep things simple. So let's say you had a tomography procedure that was given k copies of a pure state psi, right? And it outputs a classical description of another vector, theta, such that the distance between these two vectors is at most epsilon. And let's fix epsilon to be, here we'll even be generous. Let's say that the distance between the two vectors is actually, it doesn't even have to be too small, like it can be 1/2, right? So let's say that were possible, and we're going to get a lower bound on the number of copies k. And let's say that psi is a psi is a let's say psi is an n-qubit state. And the dimensionality of this unit vector is going to be, let's say it's capital N, right? It's dimension capital N. And we're going to see that if this were true, this would actually imply a communication protocol between two parties. Let's say we have Alice. Okay, she gets some classical message M, and she wants to convey this message to Bob, who's sitting over here. But instead of sending the message, she'll instead send a quantum state over. Okay. And Bob will perform some tomography on this quantum state to get a classical description. And he's going to, like, essentially Alice is going to embed this message M into this quantum state. So when Bob gets this, this classical description, he can recover what the message is. Okay. And in order for this to work, like Alice is going to have some way of mapping messages M into quantum states. And we're going to use some quantum code book idea in order to accomplish this. So what is she going to do? So Alice and Bob, before the protocol, they're going to agree on some like encoding scheme. Okay, So the encoding scheme is they're going to map classical, they're going to have like a dictionary between classical messages and quantum states. So, we're going to try to encode classical messages of some length r with quantum states psi m on n qubits. And we're going to do some calculation to see how big r can be. Like, what is the maximum length classical message that we can make? Okay. Right, so we're going to agree on the following encoding scheme. So let's say they have this encoding scheme. So what Alice would do is she's going to send, if she gets message m, she's going to send psi sub m and maybe k copies of psi sub m to Bob. So that's the first step. Right, so Bob gets this collection of qubits, right? He's going to get k times n qubits. Right, so because each psi m is n qubits and he gets k copies, so Bob is going to perform tomography. And what's the guarantee of our tomography algorithm? He gets some classical description of some state theta that's also n qubits, such that theta is at most epsilon away from the measured state. Right. So he's going to, what he sees is this theta, and he's just going to go back to this code book and say, well, which is the closest psi sub m? What is the closest psi sub m? And I'm going to think that is the message. And then he's going to output m prime as his guess for what the original message m was. So in order for, what we hope is that m prime is actually equal to m. So we need that when Bob looks through this code book, he can unambiguously recover like what psi sub m was. So what this means is okay. So what I've written here is that in order for this to be a good code book, we need that all of these different vectors, all of these different quantum states that we've associated with these messages, they all have to be kind of far away from each other, right? Like if he had two psi sub m's that were really close, then Bob could potentially get confused between the two. So we need these two vectors to be separated, right? So the question is like, what is the, what is, our goal is we want the most number of different quantum states, psi sub m, that all are far away from each other. So this is kind of like a packing problem, right? So this motivates the following. Does it make sense, like why we want to find out this question? Okay. So we just need to figure out, like, how many of these states can we pack in together? So let's draw a diagram.
Like intuitively, like if you take some sort of a quantum version of a Hamming code, it should work. But like I have no idea what a quantum version of a Hamming code is. So I don't know.
Yeah, if you studied like error correction before, this should be a very familiar idea.
Yeah.
And pictorially, it's going to be very similar. So yeah, let's draw the following picture. Let's consider, I'm going to write a little smaller because I think I'm running out of slides. Consider the space of n-qubit states. Okay, I'm going to give this a name. This is just S of C2 tensor n, right? S will stands for sphere. And that's really because like in my mind, when I picture the space of all n-qubit states, I really just think of a sphere, right? So this is what it is, right? It's the space of all unit vectors. And every point on the surface of this sphere is going to represent a different quantum state. And what I want is to find a collection of quantum states represented by these dots that are all not too close to each other. And so I'm going to draw these little disks that kind of represent like sort of like a forbidden zone around each quantum state. And these disks should not overlap. Right, and we want each disk to have radius epsilon, because like we don't want, if you fall within this disk, then you should be able to uniquely identify what's the closest point, like center point. There's a question. I think you said this, but it's an n-dimensional sphere, right? Oh, good. This is not an n-dimensional sphere. It's much, much bigger than that. The dimensionality of this space is 2 to the n, right? So each of these vectors is of length 2 to the n. And so it's the sphere of all length 2 to the n unit vectors. I think technically, like mathematicians call this like the sphere of dimension capital N minus 1. Remember, capital N was equal to 2 to the n. There's a minus 1 just because it's sort of like, since you're just talking about unit vectors, you kind of lose 1 degree of freedom. But anyways, that's just kind of like a technicality. Okay. So now like we have this kind of like geometric pictures, like how many of these disks can we pack into this capital N minus 1 dimensional sphere, right? And this is just like a high dimensional geometry problem. Does anyone have a sense of like what's sort of the order of magnitude, or like how many of these disks can you pack in?
I'm guessing about the ratio of the volumes.
Mm-hmm. And do you have like in terms of little n or capital N, do you have a
Oh, it
sense
should be
of
exponential in n, but I'm not sure about exact.
which n, little n or big N?
Exponential in little n.
Mm-hmm.
I think actually exponential in big N, but maybe I'm wrong. I don't know.
It's one of the two.
Yeah.
It's exponential in something.
Oh yeah, sorry, in big n. Yeah, in the dimension.
Yeah, this space is really huge. Yeah, let's just do the calculation. And you're right, there is some kind of like, you just want to see like what's the, we're not talking about volume, but I guess technically surface area, but you know, it's just like kind of like some volume. You want to look at the surface area of the bigger sphere and look at the surface area of the smaller disks and just do the ratio. And then you get a lower bound. So okay, so if you look on Wikipedia about these n spheres, everything's written in terms of real space. So let's just work with that just to keep things simple. I mean, it's basically similar in complex space. There's a formula for it, which is surface area of a sphere of radius r, which is good. So Sn minus 1 is equal to 2 times pi raised to the dimension over 2 divided by n over 2 minus 1 factorial. And then you have your radius raised to the power n minus 1. So that's, if we, this thing here is the sphere of radius 1. Each of these little disks, they're not spheres, they're like little caps, kind of. Like, you took the globe and you kind of drew a radius on the globe. I mean, it's not a sphere per se, but the surface area of the disk, I claim, is at most the surface area of the sphere of radius epsilon. So like, if you just sort of picture it in your head, it should hopefully make sense. So this thing is Sn minus 1 radius 1, and then the surface area of disk is at most Sn minus 1 of epsilon. Why is that? I mean, you kind of like picture, here is our little sphere of radius epsilon. But like this disk here is not like the surface area of this little ball, but it's really some kind of like, okay, this is going to stretch the limit of my drawing skills, but it's sort of like, I'm not even sure how to do this. It's kind of like the surface area of this like blue, cup. Right. I don't know, maybe someone has a better way of explaining this.
Sorry, could I ask a clarifying question?
Yeah.
So are the disks actually spheres or are they still disks?
They're not spheres. They're oh yeah, Rocky, you had a good way of so they're like what did you say? Yeah, they're like an arc of a sphere. It's like you took a sphere, but then you just kind of like took a small section of it. Like the way I picture it is like, imagine that you took you know, you're on the Earth and you're standing at a point and you just kind of like drew a circle around you. But since the Earth is curved, it's not like a flat disk. The disk is kind of curved a little bit. Does that make sense?
Yeah, that helps a lot. Yeah.
Oh, sticker on a ball. Oh, perfect. Yeah. It's a sticker on a ball. I like that. Okay, so you want to know like what's the surface area of the sticker of radius epsilon? And I claim that, okay, you might as well just say it's that like at most the surface area of the epsilon size ball. So that's where this inequality is coming from. Okay, let me add another page. I think that should... Okay, so now we just have to do the division. So we have Sn epsilon is equal to 2 pi capital N over 2, n over 2 minus 1 factorial, epsilon raised to the n minus 1. And if we do, you know, the number of stickers on the ball, well, it's going to be at least Sn minus 1 of the big ball divided by Sn minus 1 of each of these smaller things. And, you know, this is just going to be, you know, this 2 pi and factorial stuff all just cancels out. And you get 1 over epsilon raised to the capital N minus 1. Okay. So that's a lower bound on the number of disks you can pack in the space of all little n qubit states.
Hold on, just because you can, the area divides that way doesn't mean you can actually put disks that way, right? It's not like exactly the same. Like you can't use little weird spaces in between disks, for example. Like otherwise sphere packing would have been solved the year it was posed, you know?
It's okay if we have space left over. Yeah, maybe I shouldn't say pack, but at least I can fit at least these many spread out points.
I think at most.
Like I think as an upper bound, this would work really well because you can say, well, how many little spheres? By the way, this might be approximately right anyways, I don't know, but I'm saying as an upper bound, it's obvious. Like you can at most put in that many spheres. But as a lower bound, like my historical proof is that they didn't know for a long time how many spheres you can pack in a space. And if it was just divide the bigger space by the volume of the sphere, then that would not have been an open problem in math.
Wait,
so either I'm wrong about that or this is wrong.
Oh, I see. I see. Oh, okay. I see. Like this division argument is just sort of like, it doesn't care about like the arrangement of points. It's just saying like, what's the total stuff you have, and then stuff you can sort of like shift around everywhere, but you can't do that on the.
Right, you can't actually do that.
Yeah.
But the amount of area you're left out with is just a constant factor of what you, like if you're trying to pack them as as dense as possible. You're only going to this constant factor. And should, I think it should, that's all.
Yeah. I see. But I take your point. Yeah. Okay. So this is not an exact lower bound. Okay, that's a good point. But sort of it's asymptotically true. So maybe up to some constant factor or something. Okay, so good point. I'll make a note of this. This is a heuristic argument. Okay. For the reasons you mentioned. Yeah, and just sort of to like say what you said again, it's sort of like, imagine that like, you know, you cut out all these spheres or these discs on a piece of paper, and you had like all this leftover stuff, like all this leftover paper, but you can't actually fit in another disc on that remaining paper, even though you technically had enough surface area. So that's kind of what's wrong with the argument I gave. Okay. That's a good point. Okay, so next time I'll find what the correct argument for this is. But it turns out that this number is still the correct number. Okay. That's like the main conclusion that I wanted to present. Okay, there's a question. Why is it a lower bound, not an upper bound? We want a lower bound just because we want to say like, you can, there's many, like this code book can be made really large. So if Alice wants to send k copies of an n-qubit state over to Bob, then the number of possible classical messages that she can try to convey is going to be at least this much. Let me add another. Yiming, does that make sense? Okay, great. So, and here's the thing that's kind of stressed, like the space of n-qubit states is huge. Like the number of these disks is going to be doubly exponential in little n. Okay, so if epsilon was equal to half, as we said, then this is equal to, you know, roughly equal to 2 to the 2 to the n different classical messages, right? Which is a absolutely ginormous number. So the number of bits is going to be log of this, you know, roughly log of 2 to the 2 to the n, which is equal to 2 to the n. So this is roughly the number of classical bits that Alice will be able to convey to Bob using this quantum codebook. Okay. So so what's the conclusion here? Can convey 2 to the n bits using k times n qubit messages, which sounds pretty amazing. Like if k is small, like if the number of copies of the state you need to send over is small, then like you can compress vast amounts of information in these quantum states. But that's too good to be true, and that's due to something known as Halevo's theorem. All right, and this theorem places fundamental limits on the ability for quantum states to convey classical information. So I'm not going to write down the formal statement of Halevo's theorem, but I'll just say what we need to conclude this argument, which is that max number of classical bits that can be reliably encoded into n qubits is n, right? Which is like kind of a striking statement, at least when it was first discovered, because you think n qubits, well, this is a 2 to the n dimensional vector. Why can't I store 2 to the n classical bits in it? I mean, you can try, but because of measurement and things like that, you won't be able to recover the information you want. And Halevo's theorem formalizes this. So so applying Halevo's theorem, what Bob received is a kn qubit message. So kn has to be at least 2 to the n, right? Because he was somehow able to decode this message m, which tells you that k must be at least 2 to the n over n. Right, the number of copies that Alice must have sent to Bob for him to decode this message must be exponential in little n. So sort of just to unroll everything back up, we were originally talking about tomography, like how many copies of a quantum state do you need to get this classical description? You need an exponential number of copies.
Is this known to be tight? Like, I guess you can do it with 2 to the n in some quote unquote easy way, but like, is 2 to the n over n known to be tight?
This is a great question. It's unknown. So yeah, there's a gap. And yeah, I'll get into this, I guess, next time. Yeah, next time we'll talk about like different tomography procedures. Like I'll talk about a really simple one that gets like really bad bounds, and then another one that gets better bounds, but we still can't, we don't know if this lower bound is still the best on the number of copies of a state you need to obtain its classical description. Okay, so yeah, we'll pick this up next time. Yeah, and we'll be in Chandler 401, so hope to see you there.
Thank you.
Yeah, thanks everyone.